Hello, this is Miss Nichols, and this video is on atoms, subatomic particles, conductors, and insulators. The essential question for today's video is, what are subatomic particles, which I think you probably heard of, but maybe not by that name, and how do they behave in different materials? So let's start with talking about atoms, which is a word I'm sure you heard in a previous science class. Atoms are the building blocks of matter. They're basically the smallest piece. It's like the Lego piece of everything that you see around you. And so if you start off with like an image of an ant or something, and you zoom in, you're going to get to the cells of the ants. If you zoom in far enough, you get to these little tiny pieces that fit right together, and those are the atoms. There are 115 types of atoms, and you're probably familiar with many of them. Those are known as the elements, such as helium, carbon, and the like. Every atom is made up of some combination of the subatomic particles. Subatomic particles are protons, neutrons, and electrons, and the word sub, of course, means smaller than. So those are the things that are smaller than atoms. They make up the atoms. And each of those different elements has a special characteristic combination of the protons, the neutrons, and the electrons. Each of the subatomic particles, the protons, neutrons, and electrons, has mass. So this is where the mass of the universe comes from. It's the sum of all the masses of these protons, neutrons, and electrons. So while everything around you looks really different, it's actually made up of just those three things. And those subatomic particles also have a new property, which we're going to be talking about in this unit, known as charge. And maybe you're familiar with it, but we'll definitely do a lot more work with it as we move forward. So let's make a little table to compare and contrast protons and electrons. Protons have a lot of mass compared to electrons. They're actually the largest component of the mass of atoms, whereas electrons have teeny tiny mass. So if you took out all of your electrons and put them on a scale, and you took out all your protons and put them on a scale, your mass would pretty much be made out of protons with a tiny bit of electrons. The protons are stuck in the nucleus of each atom, so they're kind of bound together in like a little ball or packet. They're stuck right there. And the electrons, on the other hand, can orbit or move. They can go from atom to atom. So they're like way on the outside of the atoms. They're tiny, fast little things, and they can move around from atom to atom, whereas the protons cannot. Something pretty dramatic actually happens if you try to pull a proton out of the nucleus. It's called nuclear fission, and it's the foundation of nuclear power and also nuclear weaponry. So we don't want to pull any protons out of the nucleus. If we do that, we've got nuclear explosions. Electrons, on the other hand, you can move them around anywhere you want. Protons are going to have what's called a positive charge. You can remember p, and the charge on a proton is, we're going to assume in this class, it's known as +1 Coulomb. We'll talk about that in the next unit a little bit more. That's actually a bit of a lie, but it's a simplification for this class. And electrons, what you need to know about them is that they have a negative charge, so they have the opposite charge from a proton. And in this class, we'll call that a -1 Coulomb. And we'll talk again more about that unit in a little bit. Protons and electrons and atoms in general are held together by a force. So a force is something that pushes or pulls things together. And they're held together by something called the electrostatic force. And I would use that in an equation as an F with a little e next to it. Alongside with the gravitational force, which probably you guys are familiar with, the electrostatic force is one of the fundamental forces of the universe, which means it's a big deal. It governs almost everything around us. The strength of the electrostatic force between two objects has a linear relationship with how much charge the objects have. So the more protons or electrons an object has, the more sigma charge, so the more total charge the object has, the stronger it's going to be able to push or pull things by this electrostatic force. And the force also has an inverse relationship with the distance between two objects. So if you have two charged objects and they're really close, they're going to be pulled together stronger than if they are really far apart. And we'll do some demos with this in class as well. One note about this, and you probably are familiar with this idea if you've ever played around with magnets, but it's the same thing with electricity. And again, we'll do this in class. If you have two objects that have opposite charges, so one of them is positive and the other one is negative, they're going to attract each other, which means they pull towards each other. And on the other hand, if you have two objects that have the same kind of charge, so they either have both negative charges or they have both positive charges, those objects repel each other or push apart. So the force, the direction of this electrostatic force depends on whether the two objects that we're dealing with have the same kind of charge and they're pushed apart, or opposite charges and they're pulled together. Okay, so now that we've talked about what makes up an atom, let's talk about why we care about them in the world around us. One of the main implications of the way atoms are built is a property known as conductivity. Conductivity is how easy or hard it is for the electrons to move from one atom to another. Remember, we said those electrons could move around, and it turns out the movement of electrons impacts lots of things in our lives. If anything that you've ever plugged into an electrical socket depends on electrons being able to move. So understanding conductivity is pretty important. The number of protons in the atom determines what element it is, and also determines how conductive it is. So it's interesting that the number of protons determines how easy it is for the electrons to move in or out. And that may kind of make sense to you if you think about the fact that the protons are positive, the electrons are negative, so they're attracting each other. So how many protons we have determines how hard we hold on to our electrons. This is just a chart. You don't need to have this whole thing written down, but you probably have a sense of this, of materials that are good conductors and materials that are not good conductors, otherwise known as an insulator, which we're going to be talking about in a little bit later on. So a good conductor, electrons move really easily through something like silver or copper, and not as easily through rubber, glass, or wood. As I mentioned, the word insulator refers to a material that has a low amount of conductivity. One way to think about this is something that you could safely stick in a light socket, right? So those little child safety things are designed to be stuffed in light sockets, and they will not electrocute you, and they will not electrocute anybody that touches them. They're made out of plastic or rubber, so they're really safe to put into a light socket because electrons cannot move through them very easily. The reason they don't move through these materials is that the nuclei, where the protons are, the nucleus of the atoms, hold really tightly to their electrons. They can move around, electrons can move around inside the atoms, they can orbit, but they can't escape easily. This is kind of a schematic picture of a chunk of an insulator. It's got 9 atoms. Those atoms are really simple. They just have 1 proton and 1 electron each. But you'll see that each of those electrons is staying near one of the protons. So in each chunk, in each atom, we have 1 proton and 1 electron, and the electrons can't really move from atom to atom. That's pretty representative of an insulator. Some examples, as we saw on the last page, are wood, rubber, plastic, and the like. So on the other end of the spectrum is a conductor, which is a material with high conductivity, not surprisingly, aka something you should not stick in a light socket. This is actually an electrical hot dog cooker that I own that is a terribly dangerous thing. I literally have taken a power cord and I have cut off one end of it and I have stuffed it into 2 ends of the hot dog and plug it into the wall, and it cooks that hot dog really fast. I bet you're not surprised by that. Normally in a normal year I'd be doing that in class, but for now you'll just have to imagine Miss Nichols sticking a hot dog in a light socket. Please do not do this at home. But hot dogs are conductors, right? They're made out of the same kind of material that your skin is made out of and your flesh is made out of, and we know it's not safe to stick those into a light socket either. So what happens in conductors? Well, the atoms are willing to share their electrons with each other. They can move anywhere in the material, and they can also easily move on and off the material onto other conductors as well. So this might be a picture of a conductor. The different colored bands don't really mean anything. I was just trying to make sure you could kind of see what was going on here. But the idea is there's 9 atoms in this as well. There's 9 little proton nuclei, but the electrons are not like 1 to 1. They're moving around wherever they want to be. They might be bunched up on one side. They might be bunched up on the other. They're probably mostly kind of spread out, but they're not locked into their atoms. Some examples of conductors are metal, water, hot dogs, those kinds of things. Okay, this is the end of the video. Please take a minute and revisit the essential question. What are subatomic particles and how do they behave in different materials? And take a minute to read that Calvin and Hobbes on your way out. Thanks for watching.